Welcome to this explainer. Today, we're diving straight into exactly how engineers design, optimize, and most importantly, safely test the complex electronics that power literally everything we do. Whether we're talking about the phone in your hand right now or the massive power grid keeping your lights on, it all starts with one absolutely foundational step: translating physical reality into a virtual simulation.
Have you ever actually stopped to wonder about this? Before an engineer ever solders a single piece of wire or plugs in a power source, they already know exactly how that circuit is going to behave. They know how fast it'll charge, how much heat it's going to give off, and if it'll actually filter out electrical noise safely. Well, today, we're uncovering the computational superpower they use to pull this off, turning raw, unpredictable physics into totally predictable, actionable data. All right, here's our roadmap for today. We're going to cover the magic of RC circuits, meet something called the time constant, break down the math behind the charge, and then see how we actually simulate reality in MATLAB and Simulink. Finally, we'll wrap up with why this kind of simulation is absolutely crucial today. We've got a lot of ground to cover, so let's get right into it.
Section 1. The magic of RC circuits, from camera flashes to battery chargers. So we're kicking things off with a massive building block in electronics, the resistor-capacitor, or RC circuit. To picture this, just think of a plumbing system. The capacitor is your water tank, storing up energy, and the resistor is the pipe that dictates exactly how fast that energy is allowed to flow.
Just think about the messy, physical reality of a real circuit board for a second. You've got copper coils everywhere, soldered joints, physical capacitors and resistors just sitting there on the board. This is where every single engineering challenge starts. It's totally tangible, and honestly, it's pretty chaotic. Trying to predict what the board will do just by looking at it is pretty much impossible.
So to actually tame all that physical chaos, engineers take a really crucial first step. They abstract those physical, soldered-together components into a super clean mathematical model, a schematic diagram. All of a sudden, that messy tangle of wires becomes a really elegant set of logical relationships. Everything has a distinct mathematical role. This abstraction is basically the gateway we have to pass through to get to simulation.
Section 2. Meet the time constant, the heartbeat of the circuit. You see, every RC circuit has an internal speed limit that dictates just how fast that theoretical water tank fills up or drains out. And that brings us to the main character of our story today.
The crucial thing to remember here is the time constant, represented by the Greek letter tau. It is literally the heartbeat of our circuit. You find it just by multiplying the resistance by the capacitance. That's it. But if you change either of those two things, you completely change the heartbeat of the system. A tiny tau means your circuit charges lightning fast, while a big tau gives you a slow, steady buildup of energy.
Now, here's where it gets kind of wild. The laws of physics specifically dictate that in exactly one time constant, just one tau, a charging capacitor will hit roughly 63.2% of its absolute maximum charge. And the crazy part? It doesn't matter if we're talking about a capacitor the size of a building on the power grid or a microscopic one inside your phone. That 63.2% is a universal rule of nature. But there's a flip side to this. At the exact same time that charge is building up and pushing back against the power source, the current flowing through the circuit is dropping. At that exact timestamp of 1 tau, the current falls to roughly 36.8% of its starting value. So charge goes up, current goes down. It's this perfectly balanced, complementary dance.
Moving on to Section 3, the math behind the charge. Here's where we use exponential equations and Kirchhoff's laws to really lock down exactly how our system behaves over time.
We use this exponential equation right here to describe that charging behavior. I know, it looks a little heavy at first glance, but it tells a super intuitive story. The charge skyrockets at the very beginning, and then it smoothly tapers off as time goes on, getting closer and closer to max capacity without ever perfectly reaching it in theory. It's just a beautiful curve of diminishing returns.
Okay, so the math gives us the absolute rules of the road. But here's the massive problem we run into. Figuring this out over thousands of split-second time steps to map the full curve, that requires an unbelievable amount of calculation. If an engineer had to do the calculus by hand for every millisecond of a charging cycle, they'd spend their entire career testing one single design. We absolutely need a computational powerhouse.
And that brings us to Section 4, simulating reality in MATLAB using the finite difference method. This is exactly where software swoops in to save the day, predicting the circuit's future one tiny fraction of a second at a time. So, instead of forcing the computer to solve continuous, mind-bending calculus, the software relies on this incredibly elegant three-step algorithm. Step 1. Set the starting line. Like saying, hey, at 0 seconds, the capacitor has 0 charge. Step 2. Calculate the voltage for just the very first microsecond. And step 3, the real magic, it loops. It takes the result of the last microsecond and uses it to calculate the next one, updating constantly based purely on its previous state.
You can literally see that happening in the MATLAB code. We just use a basic for loop to crunch through the numbers. In the blink of an eye, the script calculates voltages, currents, and the charge for every tiny slice of time. As long as we keep that time step way smaller than our time constant, the simulation is incredibly accurate.
All right, Section 5, Simulink, the visual approach, where we choose block diagrams over lines of code. For engineers who prefer working in a more visual drag-and-drop workspace instead of staring at text scripts, Simulink is a total game changer.
Now, when we compare these two approaches, it's absolutely vital to understand they are describing the exact same physical system. Whether you are typing out differential equations in a script to step through time numerically, or you're connecting visual transfer function blocks with your mouse to model it graphically, it doesn't matter. You are simulating the precise same physical reality.
There is a really critical detail when you're building this out visually, though. You have to use the integrator block for the capacitor. Why? Because the voltage across a capacitor is inherently the mathematical integral of the current flowing into it over time. If you accidentally used a differentiator block, it would be mathematically wrong. The integrator perfectly models that physical accumulation, just like water filling up our tank. Section 6. Why simulation matters today for safe and optimized engineering. Let's bring this all back to reality. Mastering this pipeline from a messy copper board to pure math, into MATLAB code, and finally into visual Simulink blocks is non-negotiable for modern engineering.
By totally nailing these simulations before anything gets built, engineers are pulling off some incredible stuff. Sure, they're saving a ton of time and money, but they're also preventing catastrophic failures like actual electrical fires during testing. They can optimize your laptop charger so it doesn't ruin the battery cells. They can control the split-second timing for industrial strobes and refine the filters that stop your electronics from frying. It pretty much guarantees things work safely on the very first try. Which leaves us with a pretty fascinating thought to chew on. Today, we've seen how to perfectly translate a simple RC circuit into a virtual world. But as our computing power explodes and our tools start integrating machine learning and massive data sets, what impossible physical systems are we going to be modeling next? If we can simulate the heartbeat of a simple circuit today, is it really that crazy to think tomorrow will simulate the heartbeat of an entire city or even a planet? Thank you so much for joining me for this explainer. Keep questioning, keep learning, and I'll catch you on the next one.